So I should thank the organizers for inviting me to this workshop, and I am looking forward to hearing from many of you. So today I have been asked to give some set of pedagogical lectures on some of the interface between string theory and hydrodynamics. It's a subject which has been going on for almost quarter a century, and so I would kind of like not be able to do full justice to it, but I wanted to kind of give a broad overview, and that is, I think, also the intention of the organizers. Okay, I've been given 1 hour 50 minutes. I've kind of arranged my talk into some two distinct lectures. Okay, so around of equal length, about half an hour, also 1 hour each. So first, I would like to talk about holographic fluids. So I'm giving a board talk. So if what I'm writing is not legible, or if you have some questions, please free to say. So holographic fluid dynamics, or as it is also known sometimes as fluid gravity correspondence. Okay. So most of this is somewhat old stuff, slightly more than a decade old, which was developed from roughly starting from 2000s and till 2010s. Okay, so this would be my first thing, which is why fluid dynamics and gravity are very close related, and what do we mean by fluid gravity correspondence, and how it kind of maps various things, like in fluid dynamics to Navier-Stokes equations and so on, to Einstein equations in a particular kind of black hole background, which I'll describe. And the next hour, okay, I'll spend on fluctuations in this context. Okay, now this is a somewhat old subject and well understood. Fluctuations, there are some results, but I think many of this is not completely clear. Okay, so this is more newer stuff, and so this will be the second part would be more would have more open questions and things that none of us understand and so on. Okay, so that is the rough division. Okay, so let me kind of start with some broad motivations. Okay, of thinking about why, let's say, I think about fluctuating hydrodynamics, and why I think it is important and interesting, and the kind of questions that I think are still unanswered and open. Okay, so I think what one thing that I would like to have is motivation, and just to see where we are going. Okay, so one thing would be to have a systematic framework. Okay, for fluctuating hydro, so or fluctuating fluids, let's say. I will kind of use them interchangeably as it is usual. Fluctuating fluids. Now, this is a subject that many people here are aware of and so on. Okay, so I think in the general spirit that maybe symmetries will help, one can probably kind of reduce this problem to somewhat more symmetric situations. For example, you can ask, say, for relativistic fluids, which are somewhat more constrained, okay, framework than, or you can even further kind of add a symmetry. Okay, you can say relativistic and plus conformal fluids. Conformal means, for people who don't know, scale invariant. Okay. So this is a kind of, I think, one of the simplest contexts. And even in the simplest context, we don't quite understand, like what happens. Especially, like what we want is something at full nonlinear level. Okay. So fluid dynamics, as you know, is a nonlinear PDE and a nonlinear set of equations. And it's very natural to expect that its fluctuations are also nonlinear, that the noise, so to speak, in fluids is also non-Gaussian, okay, in general, okay. So it has some higher correlations and some very interesting structure, okay. And the question is that, what characterizes it? And one question you can ask is that what additional data do you need? Let us say you are given some fluid with some viscosity and so on. Is it enough to specify the kind of noise and fluctuations in that fluid? Or, do you need more additional data? I think these are all very interesting questions. And these are things that I and many other people have worried about for a long time, but without a very clear answer. Okay, and so I talked about nonlinear level. At linearist level, there is some understanding at linearist level, okay, of these questions. Okay, for example, at linearist level, you can just think of there being a Gaussian noise. Okay, that is kind of natural in a linearist theory, and its strength is basically governed by standard fluctuation dissipation relations, governed by, let's say, fluctuation dissipation relations. Basically, what I have in mind is some analog of these Einstein-Smoluchowski relations in the Brownian motion and so on, where basically what you say is that the fluctuations in the fluid are related to the parameters which control the dissipation in the fluid, which are controlled by viscosities, and if you have some charged fluid, conductivities, and so on. Okay, and you expect there's some general expectation. Okay, that since fluid is a thermal thing and fluctuations in thermal states, we expect some kind of a fluctuation dissipation relation, which kind of governs the noise. Okay, there with the dissipative parameters there. Okay. Then there's also a question of if this is also related. Okay, these fluctuations are also closely related to discussions about what are called long time tails. Okay, or memories. Okay, in the sense that if you look at correlation functions in a fluid, you would. Fluid dynamics tells you that things die down. Okay, exponentially fast. But then there are some power law correlations in some sense, like in the conserved quantities, so which are what are called as long-term tails. So I'm being very crude here, okay, but these are the kind of questions I want to kind of situate this discussion in. Okay, so we kind of know, I will talk in my second half of the talk, what we do know, especially in this holographic context, about these long-term tails and memories and so on. Okay, in these things again, at a linearist level, we have some understanding, okay, of how these things come about. In the high energy theory parlance, we say this is like the fluid modes running in loops, okay, and they kind of give rise to some long-term tails and so on. Okay, so broadly speaking, the question about this full nonlinear level stuff is to kind of take these kind of results that are already known and generalize it, okay, and kind of give a systematic framework, okay. So people who come from field theory and so on, okay, we would say, given effective field theory description. Effective field theory or EFD description. in the sense that, so in field theory, effective field theory is basically you give a set of parameters and you kind of have a complete set of parameters which kind of captures all kind of fluids and so on. And what we would like to know is what are those parameters, okay? And in terms of those parameters, how do we calculate the physics of these things, okay? What is the noise? What are the memories? What are the tails and so on, okay? And this is a broader question. I think like I'm interested in, okay? And this general thing about holographic fluid dynamics, okay, kind of takes these broad class of questions, okay, and then relates them to, so let me call this fluid gravity correspondence, okay. So let me call this as FG, okay, just to not to repeat. So this fluid gravity correspondence basically relates these things, okay, to like questions in gravity, questions about black holes and gravity, okay, and that is interesting. Now, it's an open question on whether by relating it this way, okay, are we kind of like understanding better, or have we kind of solved these things better, okay? That's still open question, okay, but at least I think it brings like new insights, okay, by relating it to black holes and gravity, and this is and that also maybe Hawking radiation, okay, which is the way fluctuations show up in black holes, okay. So things that like people who work in quantum gravity and so on, okay, they like and love, okay. So the point here is that like one hope is that like by kind of doing this mapping, okay, you kind of understand better the fluid dynamics, okay, or like another hope might be that you kind of understand on the fluid dynamical side these questions, and those questions can tell you about things like Hawking radiation and what happens like about like quantum fluctuations near black holes and so on, okay. So fluctuations around black holes, okay, and like that is obviously a very interesting question for people who are interested in quantum gravity, okay. And it might even be like if we are lucky, it might even be the way the first quantum gravitational effects could be observed. One of the major problems in quantum gravity is that we do not have any kind of experimental probe into it, okay. And maybe like if you have fluctuations around black holes and those things, like if you kind of have them imprint themselves on some signal, some astrophysical signal, gravitational wave signal, and so on and so forth, okay. The hope is that maybe you can say something about like what is happening around black holes beyond the classical theory of Einstein about gravity and so on, okay. So that is a like broad hope, okay. Whether any of that is will work is a question, but I think like these set of ideas, okay, have been very motivating for many of us to study these questions and so on, okay. So that's a kind of like broad framework, okay. So now I would like to kind of talk about how that works, okay. First at the level of ordinary fluid dynamics, okay, for an hour before going to fluctuations and so on. But before that, are there any questions, comments at this point? Okay. Okay. Okay, fine. So,
sorry, Loga. So so you want to say that one could detect presumably Hawking radiation by looking at this imprint, as a fluctuation of.
That's a hope. There are some fluctuations around black holes, okay, which may be it shows up in some astrophysical thing. It could be gravitational waves. It could be some of these jets and things like that. Okay, we do not know, because we do think that there are black holes in astrophysics and they have a lot of violent process happening around them, okay. Sometimes very high energy processes like gamma ray bursts and things like that, and in the case of gravitational waves, there's a merger and so on. These are all very high energy and very non-perturbative. But the question is that like whether there are any there's any hope at all of discovering some signature of underlying quantum nature of gravity from them. Okay, because you do expect, like from various kind of quantum effects that there should be fluctuations. Okay, and they are very closely related to thermal fluctuations as on the side of fluid dynamics. And the question is that whether there is some statement, especially, or maybe like something about this time, if you really understand these long time tails, memories, right, or something. Like at this point, it's all very speculative. But that's a broad motivation. Okay, for kind of, I think, but I think it's a very important motivation to try to kind of understand these questions and take them seriously and try to address them.
Thank you.
Okay. Anything else? Okay. So now let me talk about what is called as a fluid gravity correspondence. Okay. So this, as I said, is an old subject. Okay. And I won't be able to give you all the references and so on, but I will refer you to these reviews. Okay. One is a set of lecture notes by Mukund, okay, which is in archive. On fluid gravity correspondence, okay, 4352. And then there's a review which was written by Veronica Shiraz and Mukund, okay, which is also kind of summarizes these things, okay, as they were, okay, and its archive number is this, okay. So I won't kind of like say who did what and all the very interesting history, okay, because that's the thing. But so these are all, there's a review, okay, and there's a lecture notes, so you can find like to some extent the history of the subject and various kind of things that there are. Okay, so I will kind of like just confine myself to some basic things, basic ideas that go around in this fluid gravity correspondence. Okay, so the basic point here was something called as ADS-CFT or holography. Okay, sometimes also known as gauge gravity correspondence. Okay. So, which is something coming out of string theory and so on, which says something like this, that let's say you have some field theory, okay, living in some space, let's say in Minkowski spacetime, some flat spacetime, okay. So this, let's say it has a spacetime dimensions d, okay, I'll denote by d, okay. It could be 3 plus 1, 4 dimensions, okay. Then, like some of these field theories, okay, can be mapped, okay, to a kind of a gravitational bulk. So let me, it's a good job. So this is a field theory is just living. So you have some gravitational bulk, okay, which is basically somewhere where there's a gravity in it, okay. In particular, it is what we call as a ADS spacetime, okay, which is basically a contracting spacetime. So many of you might have heard, okay, that we live in an expanding spacetime, okay. So like if you and part of the reason we expand and the expansion is accelerating and so on, okay, is because we have something called as a positive cosmological constant, which is a statement that the vacuum that we live in, okay, the empty space, if you go out in the empty space, has some positive energy density, but you can give the vacuum a negative energy density or a negative cosmological constant, and then you get this ADA spacetime. So these are contracting spacetimes, okay? So these are not like the real universe, okay? But they have, like some good things and very nice things about them, okay? Which is the reason we kind of study them, okay? As good toy models and so on, okay? So the statement here is that, like the dynamics of this field theory, okay, are in one-to-one correspondence with the gravitational bulk. Okay, so in this gravitational bulk, there are various things. There are, there's Einstein equations. Okay, in general, there is some string theory. Okay, though that won't play much of a role for now. Okay, and of course, Einstein equations. Wherever there are Einstein equations, there are black hole solutions. Okay, so in particular, we would be interested in a particular black hole solution. Okay, so we can kind of like construct a planar black hole. Okay, so again, this is the space in which the field theory lives. So this is actually a d+1 dimensional space-time. Okay, so which is what is figuratively denoted here. Okay, in the sense that apart from like the normal time and the space, like there's some radial direction. Okay, which is not part of where the fluid lives, okay, in some sense, and the field theory lives. And this field theory is what contains the fluid, okay. So in general, the field theory, okay, you can take a fluid state in the field theory, okay. Usually this field theory, okay, is a gauge theory. It's something which is like QCD or somewhat like electrodynamics and so on. So what you mean by fluid here is that you just take a plasma, okay. Sometimes in comparison with like what we get in when we kind of bang like nuclei together and melt them, okay. If you bang them at very high energies, you melt them and you get a fluid, okay, which is usually called as a quark-gluon plasma. So sometimes you will see people calling that quark-gluon plasma. It's just if you don't know what quarks and gluons are, it doesn't matter, but it's just a plasma in the sense that it has something like electric and magnetic fields and charges, and then it and like all plasmas, it behaves like a fluid. Okay, so that is what happens to the field theory. And if you take that state, okay, what happens in this bulk, the corresponding thing is that like you get drawing skills. You get like a black hole, okay, a planar black hole, okay. So you should think of this guy as the inside of the black hole, okay. This guy is outside, and this is the horizon of the black hole. So you can think of this as r equal to infinity. Okay, so if you think of r as going like this, okay, and this is some r equal to rh. Okay, so basically, like there's a corresponding state, okay, which is basically given by a black hole. And very interestingly, these black holes actually have a temperature. That's what Hawking told us. And this black hole's temperature, okay, there's a formula by Hawking. Okay, so the Hawking's formula for this black hole's temperature actually is somewhat like this. Okay, so T is like okay, this constant don't matter. This is just something in some units. Okay, basically T goes like RH. Okay, the temperature of the black hole. Okay, goes like RH. So as you make the black hole bigger in some sense. Okay, like if you stay here and you throw in stuff. Okay, you can imagine standing here and throwing in stuff. Okay, as you throw in stuff, like the black hole becomes bigger and bigger, and it comes up. Okay, and as it comes up, it heats up. Okay, so that's a bit like like taking a fluid and dumping energy into the fluid. Okay, and then like the fluid heats up. Okay, and its temperature increases. Okay, so this is the basic like framework. Okay. Of ADS-CFT, which says that like if you kind of take some kind of field theories and look at their fluids made of them. Okay, the details you will see don't matter much for this talk. Okay, to understand the basic idea is that there's some fluid, okay, which you should imagine as living at this plane at some r equal to infinity. Okay, and and this can be rewritten in terms of a black hole or a black brain, as some people call it, because a planar black hole, okay, with some horizon and so on. And this, of course, solves this is a solution of the Einstein equations, okay, that kind of govern it, okay, and this point of this contracting space-time and so on is to basically stabilize this planar black hole, okay, and it basically makes it stable, and it makes it much more closer to fluid than otherwise. Okay, that's the point of these things. Okay, so that's a broader framework. Okay, so so the idea here is that you kind of look at various kind of waves in this plasma, and that will correspond to some kind of waves and various kind of perturbations, okay, of this black hole. And the statement is that we expect this this plasma, when if you perturb it, it will flow, and it will flow according to Navier-Stokes equations and so on, some relativistic version of Navier-Stokes equation. And the statement is that this black hole's dynamics is also governed by something very similar. Okay, and that is the basic idea behind fluid gravity correspondence. So I will write some maybe some equations and so on, but is the general idea kind of clear? Okay, okay. Let me say one more thing. Okay, so the way this works is actually very interesting. Okay, the way it works is that if you take some, let's say, a blob of fluid element. Okay, so let's say you take this fluid and you take you consider some time and some small volume. Okay, and you can consider a fluid element, as we say in fluid dynamics. Okay, and this fluid element, corresponding to this fluid element, okay, you can ask, and the way this mapping works is that this fluid element, you can kind of stand at the fluid element and you can kind of shine a beam, okay, by a beam of light or something, okay, something which is traveling at speed c. So you can throw in a beam. So this is like a beam, okay, thrown in from the fluid element, okay, and in some sense, the data of that fluid element, in the sense that the velocity and the temperature of that blob, okay, is contained in this beam, okay. So this is a beam, okay, which is kind of traveling at speed c and falling into the black hole, okay. And the point here is that so similarly, every blob of this fluid, okay, has a corresponding beam, okay. And the point is that in some sense, as we shall see, if you kind of create a fluid configuration where the velocity changes from place to place, from time to time, okay. So similarly, the corresponding data in these beams also change, okay, and those things stitched together form these black hole, okay. So that is the thing. So this is like a infalling beam, okay, of beam moving at the speed of light, okay, moving at c, okay. So the point here is that somehow the data about the fluid, the way this map works, is that the data about this fluid is kind of contained in this space-time, okay, so blob by blob getting mapped to beam by beam. Yeah. Data, for example, data in fluid dynamics is like a velocity at a particular point, around a particular point, temperature of the fluid element, maybe chemical potential, density. These are the things that are the fluid dynamical data, pressure, right? Okay. Frequency, no, there's no, well, okay, yeah, so if you do some perturbations at some frequency, of course, these things also will kind of, say, go at the same frequency, okay, but I'm not talking about just the frequency, okay, I'm talking about fluid dynamical data, okay, which is the kind of thing that I specified, which you, by the state, the data that you give to specify the state of the fluid, where you say the pressure distribution is somewhat like this, velocity distribution, densities, and so on. Okay, how are they? Okay, and the point here is that like those guys are mapped to these things. Okay, so what I want to kind of tell you is how this works in detail. Okay, in the rest of the talk, but I think but this is the basic idea. The basic idea is that like we take fluid dynamics, okay, in somewhere, and then we kind of use that fluid dynamics to kind of construct a particular kind of a black hole, okay, and which solves the Einstein equation. So the fluid solves Navier-Stokes equations, and the black hole solves the Einstein equations, and the kind of crux of this idea of how this construction of the reconstruction of the black hole from the fluid works by this, that you take blob by blob the data of the fluid, and you construct like various kind of beams inside, okay, inside this black hole space-time, okay, and you kind of stitch them together into the data of the black hole, okay, and that is the basic idea. Yes, yeah.
So now you're reducing.
Yes.
So at what level is that there's some difference that the state is correspond to quantum theory?
Well, as far as fluids are concerned, we are talking about high temperature fluids. At some level, we don't care whether like when we pour water, I mean, we can do Navier-Stokes equation, and Navier-Stokes did not care and did not know that there's something called quantum mechanics. Okay, but because fluid dynamics works universally, right? It doesn't matter. Okay, at least in these kind of fluids, at least in these high temperature fluids and so on. Okay. If you have superfluids, there's a separate class of fluids where the quantum mechanics might become important, but at least in these kind of fluids, okay, just fluid dynamics and whatever gives rise to fluid dynamics, the macroscopic description is in terms of some kind of relativistic Navier-Stokes. Okay. The time direction, just the time direction in some sense kind of goes along, in the sense that the time here is the same as time here. Okay. For example, you can there's a time translation invariance here, time translation invariance here. If you look at the frequencies, okay, you can kind of assign, you can label modes of this fluid by some frequency. Okay, if you're doing some linearized analysis, and similarly, you can, as I'll say, you can label these things also by this frequency. But the main difference is that the frequency is like the frequency measured from far away from the black hole. Okay, which is not same as frequency measured near the black hole, okay, because there's something called the gravitational redshift, okay, which kind of means that if an observer is sitting here and an observer is sitting there, okay, the same frequency wave, they will see a different frequency, but from the gravity point of view, the frequency is kind of measured from far away, okay, and that frequency is same, and that time is same, the time measured far away, the frequency measured far away is the same as the time and the frequency of the fluid. Okay, so that's the thing. So then, and similar thing you can say for all the spatial directions and so on. In fact, you can take all of them to be completely, just a flat space-time. Okay, in which case, yeah, so you just have a relativistic, just special relativistic things and no curvature or anything that fluid sees. Okay, so there's no problem with the time there. Is that? Yes. Yes, because because the black holes also evolve in time, okay, and the point here is that these two evolutions kind of match each other, okay, yeah, and you can kind of label both the evolutions by the same time. That's what I was trying to say. Okay, okay. Yes. Yeah. So I should have said. Okay. So this is the way this ADS-50 works is that indeed this is same as temperature of the fluid. Okay. So roughly speaking, if the fluid has different temperatures, that's like this horizon has comes up and down at various places, right? We can think of this horizon as having, this is like R equal to RH, but you could imagine that there's some bump, there's some trough, there are crusts and troughs. in the surface of the horizon, okay, and at some level that corresponds to, like different temperatures, in homogeneous temperature distribution in the fluid, okay.
The large scale phenomenon.
Yes.
What are the corresponding scales in this?
Yeah. So the point here is that, so here the 1D scale is this temperature, okay. So basically, like you would expect fluid dynamics to be a good description, okay, for like omega by T and mod K by T in the Fourier domain, okay. This is Fourier with respect to the fluid spacetime, the d-dimensional spacetime are much less than 1. Okay, so long wavelength, like slow dynamics, okay, compared to the temperature, to the background temperature, okay, because that's the only scale in this problem, basically, okay. So it's valid. So you can think of, like fluid dynamical expansion as an expansion in these kind of, as a derivative expansion, as some people call it, okay, or low frequency, low wave number expansion.
But Loga, you can include the effects of chemical potentials and so on.
You can include the effects of chemical potential. Yeah, so then you will have more scales. So I will not talk so much about chemical potential because I want to talk about the simplest example. But you can include chemical potential by making this black hole charged. Okay, and then like the charge corresponds to number density. And there's some chemical potential, okay. The electric potential, the voltage difference between the infinity and the horizon is somehow related to the chemical potential, okay, of the corresponding fluid, okay. Again, like blob by blob, this beam by beam kind of way, okay. But I won't talk about, but indeed you can include chemical potentials, you can do many things, okay. But I want to kind of talk about the simplest thing. Okay, so this is like a broad physical picture, okay, but I want to kind of tell you how this works somewhat in more detail, okay, so that you can kind of roughly have an idea of how this works in equations, okay. So I have to introduce some notation, okay. So let me kind of introduce some notation for relativistic fluids very quickly, okay. So there's T, of course, is temperature. In general, the relativistic fluid is labeled by some T of X. Okay, X is basically this coordinate in this thing, and then R is the coordinate, the extra coordinate. Okay, X is a coordinate of fluid dynamics. So I'm just talking about coordinates of the fluid. And if it is a relativistic fluid, you also have a u mu of X. It's a space-time vector, and such that, okay, u nu, okay, eta mu nu is just -1. Okay, so where eta mu nu is the Minkowski basically in C equal to 1 units. That's what it is. Okay, so then you have basically a fluid velocity, and this u mu is also a function of x. X can be E or capital or X vector. Okay, just to kind of situate. Okay, so these are the basic data of how the fluid looks like, and we want to also kind of to think about fluid dynamics. We want to kind of think about let's say energy density in the fluid. Okay, so which is some function of T, E of T. Okay, and you can think of pressure. Okay, which is also a function of T. Okay, and so on. Okay, you can also think about entropy, density, S of T, and like so this is a fluid without any chemical potential. So these are all related. Okay, actually just one is enough. Okay, one of these functions is enough. It's basically specifying an equation of state. That is when the fluid is at rest. It's basically the dynamics is just thermodynamics, and you just have a pressure, and pressure can you can make it give entropy by differentiating with respect to temperature, and then the energy density is given by the standard Euler relations and so on. Okay, so these two relations basically tell you that if you know, maybe I should say minus P. Okay, this kind of tell you that if you know this P, then you can get energy density, entropy density, and so on. So this is kind of like the basic data for ideal fluid dynamics, where you give like a temperature field, chemical potential field, and pressure as a function of temperature, from which you can obtain energy density and so on. Okay, so the stress tensor, okay, this is a energy momentum tensor. Okay, is basically given by something like E plus P u mu u nu plus P G upper mu nu or eta upper mu nu. Okay, so what this means is that like in the rest frame of the fluid, okay, this basically looks like E P P P, okay, which is a statement that, so this is like P X. Oh, okay, I'm kind of secretly working 3 dimensions. Okay, but anyway, 3 plus 1 dimension. So the point is that like but you can generalize it to d dimensions. So the TT component, okay, of this stress tensor is the energy density. Okay, this is very similar, and then like this is the IJ component, okay, which gives you the stress distribution, the stress tensor. Okay, with this convention that the pressure is positive stress. Okay, so it's a contractile stress tensor. Okay, and the point is that like so this is the ideal fluid or inviscid or ideal fluid. Okay, stress tensor. This is how it looks like. Okay, so and the basic equations are the Navier-Stokes equations of the fluid. Okay, are basically given by, which in this case are really relativistic Euler equations for ideal fluid, inviscid fluid. Okay, are basically given by grad nu p mu nu ideal equal to 0. Okay, so yeah, so that is the basic data for like inviscid fluid dynamics. Now, of course, like we want to go beyond that. Okay, we can start adding viscosity, okay, to this fluid dynamics, as we usually do. Okay, so for that I need to kind of define some other tensors. Okay, so usually we define something called as a projection tensor. Okay, okay, so P mu nu, which is defined as, so this eta mu nu is the inverse of that, which is same as eta mu nu plus u mu u nu. Okay, so what this does is that it projects projection perpendicular to u. Okay, in the sense that like in the rest frame of the fluid element. Okay, if you want to just take the spatial components in the rest frame. Okay, so then like you can use the projector. So if you take a vector, some space-time vector v mu, okay, and then you project it by applying this, okay, v nu. Okay, so then this is purely space-like, purely spatial in the rest frame of the fluid element. Okay, so that is that's the name of this tensor. Okay, and then there are various kind of like decompositions of the derivatives of velocity. Okay, so if you have a derivatives of velocity field. Okay, so there's a relativistic analog of the Cauchy-Stokes decomposition. Okay, so relativistic analog of what fluid dynamics is called as the Cauchy-Stokes decomposition, which is basically the statement that if you take velocity of the fluid, okay, let me just remind you in the non-relativistic fluid dynamics, if you take a gradient of a velocity of the fluid, you can decompose it into a trace, a symmetric trace-free part, and an antisymmetric part. The antisymmetric part gives you vorticity. Okay, the symmetric trace-free part gives you the strain rate. Okay, which is what, or the shear strain rate, which is what enters into Newton's law of viscosity and so on. Okay, and then you have the trace part is related to divergence. It tells you how, if you have a fluid element and it is flowing with the fluid, sometimes the fluid element can get rotated, it can expand or it can get sheared and so on and so forth. Okay, and this is the basic idea of coefficient of decomposition. So so the analogous statement here is that in the space-time is that you should also think about what happens with time derivative. Of course, the time derivative of the fluid is related to the acceleration of the fluid. Okay, so this says something like this. So minus u mu a nu. Let me, yeah, sorry. Plus, so this is a decomposition. Okay, this a nu is basically u dot grad u mu. Okay, which if you write it in terms of ordinary components, it look like u0 del t plus u dot grad. Okay. So basically, like if you write, so ordinary, it's the 4 velocity of the fluid. If you remember, your relativity is just like given by something like 1 by square root 1 minus u square and u vector by square root 1 minus u square. Okay, so then it will just be that 1 by square root 1 minus u square del t plus u dot grad, which is the standard convective derivative or something. Okay, so that acting on u gives you the acceleration. So this is the acceleration vector, 4 vector. Okay, and this theta here is the trace part. Okay, the spatial trace, which is basically theta is what is called as an expansion, which is just divergence of u, 4 divergence of u, or space-time divergence of u. And this sigma mu nu is the trace-free symmetric part. Okay, which is the strain rate, shear strain rate, or people just call it shear tensor. Okay, and this omega mu nu is what is called as the vorticity. Okay, okay, and so on. Okay, so sigma mu nu basically has, if you want to write it, it will look like this: T nu bar of grad mu bar. Okay, if you have, I mean, this is to kind of, refresh your memory. If you have seen these things, okay. If you are not seen relativistic fluid dynamics, okay, you can just look at Landau, Lifshitz or something, okay. But the point is that this is if you've not seen this before, you should just, and if you're just familiar with the non-relativistic fluid dynamics, then this is just the usual shear strain rate, which is related to del I uj, del j ui, and so on, okay. And this omega mu nu is the antisymmetric part, okay, which is the same thing, but with antisymmetric. So something like grad mu bar minus grad mu bar. Okay. So the statement is that, to describe the fluid dynamics, okay, beyond the ideal fluid dynamics, but to write down viscosity and so on, okay, what we need is this kind of tensors, okay, we generalize, okay, our intuitions from the non-relativistic context. Okay, so once you have that, okay, you can kind of start correcting this to a relativistic fluid with viscosity. Okay, so you can add dissipation. Okay, you can add viscosity basically by taking this T mu nu, okay, Navier-Stokes, to be just T mu nu ideal, or which is basically the thing that I had written here. You can also think of it as the T mu nu Euler, okay, and correcting it with something like this, minus 2 eta sigma mu nu. You can in general also put something like this, okay, where eta and zeta are shear and bulk viscosities. Okay, that's the standard thing you will see in the fluid dynamics. Okay, the point here is that since this fluid doesn't have any particular scales and so on, okay, I will not kind of explain this argument. It doesn't have any bulk viscosity. Okay, because of scale invariance or conformal invariance. Roughly speaking, this is a fluid without any other scale except the temperature, okay? And so you don't kind of dissipate any heat, okay, when you kind of expand it, okay? The point is that, so this term is not there, okay? So you just add the zeta, okay? And the point here is that, so that's a fluid, okay? And now what you can do is that, so this is what you expect on the relativistic fluid dynamic side, okay? If you have a scale invariant relativistic fluid, okay? You need to add, some viscosity, okay? And this viscosity, okay, shows up basically as, as a dissipation, okay? So once you add eta, okay, of course you have a viscous dissipation, okay? And the viscous dissipation, okay, is the idea that if you kind of create some shear, okay, and then leave it in the fluid or create some something in the fluid, okay, and leave it, then it kind of slowly dissipates, like the standard fluid dynamical story that there's a shear viscosity which kind of, dissipates these things irreversibly. So this makes the fluid evolution irreversible, okay, and the corresponding thing which happens with this in the black hole picture is that this blob, this shear, okay, creates something in the black hole, and the black hole just settles down. Okay, this is basically this dissipation, okay, gets mapped, okay, to the relaxation or decay of basically gravitational waves, okay, in the black hole background. Basically, if you kind of create some shear and so on, what you're doing is that you're by this beam by beam map, you're creating some kind of a space-time which has various, it's just a gravitational wave in it, okay, and then if you create that and leave it, then what will happen? The gravitational wave slowly dies down, it falls into the black hole, okay, and the rate at which it decays, okay, basically it decays exactly like a Navier-Stokes relativistic fluid would, and its decay, okay, and its relaxation rate, if you want, okay, kind of tells you gets mapped to the viscosity of the fluid, okay. So that's the thing, okay. So you can go further, okay. You can, so you can go further and add further derivatives and so on, further and add, more derivative terms, okay, and you can kind of keep on mapping, okay, these dynamics of this black brane to fluid gravity and so on. So to the fluid dynamics of the boundary theory, okay. So that's the basic idea, okay. So I will just tell you, how then the corresponding metric here looks like, okay, and then maybe I will stop there, okay. So the metric here basically looks like this, okay. So this is, this is just to kind of tell you. So let me remind you, okay, that this x mu, okay, are basically things in the boundary, and then there's an r, okay, which basically goes, and this boundary set r equal to infinity, okay, and when you so the basic thing is that you can write down a solution. The way the solution is written is that it is written with the u mu dx mu dr. So if you just have a fluid at rest, okay, if u mu is just at rest, okay, this just becomes something like 2 dV dr, okay, 2 dt dr plus, something plus something, okay, times dot dx, okay. You can just take something times dt, okay, and then you have this guy. You can just say it will just have x squared term, okay. So the statement is that because this time, okay, that we are measuring is this time which is called as a null time. Okay, it's measured with respect to these null beams. Okay, the beams that were traveling inwards with the velocity of light. Okay, so basically, like if you just write it, if you make kind of this vertical, as we usually do, if you make this time vertical, okay, so then these are beams which are going like that, okay, in the radial direction, okay, inwards at 45 degrees. This is a space-time diagram. That's a spatial diagram, okay, and then it's a time measured with respect to in this direction, in this null direction, okay. So it's called as an ingoing time, okay, okay, which is roughly like t plus r by c kind of, okay. So it's a time that is measured along a null direction, okay. And the statement is that, so your fluid dynamics looks like this, and the point here is that this h mu nu and this v nu are basically written in terms of these velocities and temperatures, okay. So the basic fluid gravity map, okay, so the fluid gravity map, the basic equation of fluid gravity, or the basic fluid gravity map, okay, it basically gives you these v nu and h mu nu, okay, as a functional of these velocities and temperatures of this boundary fluid, okay. And the statement is that such that, okay, this guy solves Einstein equations, okay, if these guys, if u, mu, and t solve Navier-Stokes equation. Okay, so there's a way to kind of construct this systematically, okay, which was done in these various papers in 2008 and so on and so forth, okay. And the point here is that, which is described in these reviews that I had said, but the basic idea here is this, that what you do is that you give a map, okay, which in this beam by beam way, okay, it gives you a metric in the bulk, okay, here, okay, that is, it gives you a solution of Einstein equation in terms of a solution of a Navier-Stokes equation, okay, and that is basically the map, okay, which kind of works in mapping fluid dynamics to gravity, okay. So then, this is a very interesting map, okay. So let me just say a few words, and then maybe I will conclude this part of this discussion, okay, which is that, this basically tells you that at least in a certain regime, okay, the dynamics of black holes and how they evolve and how the gravitational waves evolve, in these backgrounds, okay, are very close to Navier-Stokes equations. Okay, so basically, what another way to say it is that if you create some gravitational wave over this black hole, okay, then this gravitational wave, at least if you wait for a long time dynamics of these gravitational waves, is basically described by a Navier-Stokes equation, okay, and the way they die, okay, the way the shear in them dies, okay, and the way they flow, and all of them, okay, can be described by a very genuine and honest Navier-Stokes equation. And in that sense, you can think of this system, okay, of black holes and Einstein equations as as basically a fluid dynamical system, okay, at least in this regime, okay. So that is the basic idea behind these things, okay. I have a couple of more things to say, but maybe I will say that as a prologue to my next, next set of lectures, but next lecture. But maybe I'll pause here, okay, since it's been already an hour, okay, and ask are there any questions? Maybe we can have some few minutes of questions about the things that I've talked about. Yeah. Yes.
So I had a couple of questions. I mean, so when you write the hydrodynamics, do you think of an underlying microscopic model like here?
Yeah, so there is supposed to be, so string theory does, in very specific examples, give you underlying microscopic models out of which this coagulant plasma is made of. But the point here is that those microscopic models themselves are not very computable because those microscopic theories are very strongly coupled. They are like, they're strongly interacting, like plasma, okay. And so this is taking that strongly coupled problem, okay, and it kind of recasts it into this gravity problem. Okay, so there's a specific example where one can write down a Lagrangian and so on, but there is very little you can do with the Lagrangian. Okay, at least in this regime, because like it's a very strongly coupled theory. Okay, from which, I mean, even something like water, it's not very easy to kind of get from the microscopic theory to the macroscopic fluid dynamics. But here the job is even more difficult because the underlying theory is very strongly coupled.
Yeah, no, but at least for water, like I can think of a simple model and I can look at the conserved quantities and do something systematically, right?
Yeah.
I mean, here, I mean, like, is there a, like, do you start from a field theory and ask what are the conserved quantities and then?
Yeah,
I mean,
the conserved quantities, yes, you can read off on the microscopic theory. What are the conserved quantities?
So there are 4 conserved quantities. Is it like?
Yeah, the energy, momentum, energy. So yeah, indeed, the underlying theory is a relativistic quantum field theory,
Okay.
which has like translation invariance and all that. Okay, so which means that it has energy momentum conservation, and we also expect, because it's a local quantum field theory, we expect that energy momentum conservation is a local statement. Okay, and so you do expect some local energy momentum conservation. Okay, and there are variances like what Gautam mentioned, where you have chemical potentials, where you can kind of explicitly look at some number charge, which is inside this Lagrangian, okay, which is also conserved by the dynamics of the quantum field theory, okay, and you can kind of look at states where the number charge is non-zero or the corresponding chemical potential is non-zero, and you can relate things to that, okay, and in fact, like you can also relate, like So the answer is yes. In these, there are these very specific examples. Let's take a 3 + 1 dimensional example. One of the very common examples is what is called as n = 4 superangles theory. All that it is it's a theory, okay, of scalar fields, okay, some fermionic fields, okay, and some gauge fields, okay. So the kind of models that we often think about in particle physics, it's a like standard model and so on. Okay, so these are some non-abelian gauge fields, okay, some color gauge fields, okay. So then like so you can write down an express Lagrangian, okay, and then you can see that, and this is supposed to describe, okay, the quark-gluon plasma made of those things. Yeah. So the conserved at the level of conserved quantities and so on, indeed, we can kind of see from the microscopic theory what is expected, what kind of charges are possible, and so on and so forth. Okay, those things you can get by looking at these things, but detailed dynamics you can't solve. Okay, or rather, it's hard to solve. Okay, maybe you can solve it by some lattice or something. But yeah, is that answering your question or?
Okay, yeah, kind of.
Basically, some spin zero, spin half particles, interacting through some gauge fields, like some number of electromagnetic fields. Okay, that is the basic model.
Okay, no, so I could do this, let's say, for any field theory, right?
Not for any field theory. Okay, at least.
Where would gravity come in? Like, is there must be some specific field theories which will?
Yeah, so there are various things are kind of hidden. The point here is that like there's a string theory background to this story. Okay, which tells you that certain kind of field theories, okay, you can rewrite it as gravity. Okay, and that like comes from this argument by Nardis and so on about ADS-CFT, how these things map. Okay, but the basic idea is that like there are the dynamics of the field theory. You can kind of rewrite it, okay, by lifting it to string theory and rewriting it in certain way, okay, into a gravitational theory. Okay. You can say that large n is an input. Yeah, so there are various kind of features, as Shiraz mentions. One of the point is that like the number of species here, you take it to be very large if you want to get a classical gravity, okay, or else you get some very quantum gravity kind of setup. You also take these things to be very strongly coupled, okay. So these things are known to be very crucial to have a classical gravitational description on the other side, okay, because we know various examples and we kind of know that like what kind of things a field theory should obey to admit this kind of a description.
The thing that's sort of interesting is that
Shiraz, maybe you can use the mic. Yeah.
One thing that I find interesting is that in these large N limits, fluid dynamics becomes, in a class of large N theories, fluid dynamics as a classical theory becomes exact, with fluctuations being suppressed by 1 over N, just as a field theory statement. Okay, and that translates to it being a mapping to just classical Einstein equations in the bulk, as Loga was saying.
So it's only for field theories with a large number of
That's one of the elements.
Yeah.
That's necessary but not sufficient.
Yeah. Yeah. Are there any other questions and so on?
Yeah, so I had a couple of questions. First was like, what's the stress tensor on the bulk side now? Like we know the stress tensor here for the boundary side. So
in the bulk side, there is no stress tensor. It's actually pure Einstein equations. Okay, if that's what you're asking. So if you want, I can write down the Einstein equations. Okay, with some negative cosmological constant. Okay, I should not write mu nu. Let's write some other index. Where this AB goes over mu nu and R.
So there are no bulk fields as of now.
There are no other. There's no other matter. Okay, so it's basically like a vacuum. Okay. And there's vacuum energy. Vacuum has a negative energy density, just denoted by, maybe I should write it this way. Okay. Yeah, so denoted by the statement that there's a negative cosmological constant, which makes the space-time contracting, okay, which kind of, like stabilizes this black hole and makes this analogy to fluid dynamics really work well. Okay, that's a kind of there. But apart from that, there is no other things. You can put additional bulk. Like, for example, you can put some electromagnetic fields in the bulk. Okay, that corresponds to having some number charge which is conserved. Like, often in fluid dynamics, we want some other quantity other than energy momentum being conserved, right? Like when we do ordinary Navier-Stokes, we have the number being conserved. Okay, and similarly, so if you want some number charge being conserved, corresponding to the number charge, you can add some gauge fields. Okay, here. Okay, and then there'll be a Maxwell stress tensor, which will go into the right-hand side of Einstein equations.
The other question was on the CFT side. In general, we have to impose some conditions on the spectrum for it to be dual to like.
Yeah, this is the kind of things that we are saying, that you have to specify that they're very strongly coupled.
Right.
Okay, and it is there are a lot of there's a large N. Okay, there's a lot of species. Yeah, so these are generically expected for this kind of a nice classical description.
And just some naive question was that in the stress tensor you wrote, so classically I would at least presume that it should be traceless, but you only have the sigma is traceless here. So how would you get trace to be 0 then?
Okay. So this is traceless because this E is related to P. Okay, by E equal to 3P. Okay, equal to some e to the power B, which is some Stephen-Boltzmann law. Okay, so like what happens with black body radiation, which is also scale invariant, okay, the energy density, okay, and pressure of the black body radiation are related by E equal to 3P, and they are both going like T to the power 4, right? Okay, that's a Stephen-Boltzmann law. Okay, and if you do that, you can check that it is actually traceless even there. Yeah, which is what you expect from a scale invariant underlying theory. Okay, indeed.
I mean, so how does this fit in with the motivation that you were introducing? Like, do you linearize to solve it? And
yeah, I will talk about linearization and fluctuations in the
and the second question is, like, all the discussion even before, you said that you take and try to map it to an Einstein equation, but in the motivation you said you can also use this to understand some quantum aspects of gravity.
Yeah, you will see, because because this is large N and so on. When you start talking about fluctuations, okay, it is quantum corrections and so on. Yeah, these things. Yeah, if you still have them after I finish the next thing, like please ask again. Yeah.
Thank you.
Yes.
When we are thinking in terms of this picture, that we have a blob and we project some beam of light and that. So there, like, what guarantees us that there will be a 1-to-1 correspondence between the data in the blob of the fluid and the data encoded in the beam of light?
Yeah, it is not a priori obvious. Okay, but you can take this idea. Okay, since I'm not kind of presenting this thing, but you can take this idea and find a solution of the Einstein equations consistent with this idea. That's the point. The point here is that the eventual justification of this picture, okay, is that you can actually use this picture to actually write down equations which reconstructs this data, which is basically this V nu and H mu nu, okay. And note that I have taken my coordinates in such a way that, this beam picture is very natural because I've taken the ingoing time, infalling time, okay. And so, like I can kind of take blob by blob and I can ask, okay, if I start with some initial map, can I solve it order by order in some kind of a controlled expansion and get a solution of Einstein equation, okay, given some data which solves the Navier-Stokes equation? And the answer is yes, okay. And you can do it, and you can find explicit expressions doing it, which is what justifies this picture, okay. Yeah. So we know, I mean, this might look a bit very hand-wavy, but it can be made very precise, and you can write down equations, as you can see, like if you look at these reviews and so on. I'm not going into those details, okay, but like basically it amounts to giving these two functionals, okay, these V and H, okay, and you can indeed give them, like, so the way these are written, okay, this will work by this blob, but because of the way that I've chosen coordinates, if I give V and H in terms of U, its derivatives and so on, okay, and then you think about what that means, you realize that it means what I'm saying, that, like there's every blob is mapped to a beam, okay, basically.
Hello.
Yeah.
Yeah, so is it correct to say that I can take any solution of the Navier-Stokes equations in the 4D manifold and then kind of continue it in the 5th dimension, and there will be a unique extension possible, and it will correspond to something or the other in the 5 dimensions?
Yeah, and it solves the Einstein equations in the 5
So very
dimensions.
good. So if I take some simple known solutions of the hydrodynamical equations, then can I learn something about what happens to the black hole in that case?
Yeah, people have looked at such things. Like one thing is just, for example, one simple thing is that you can, if it was not flat space, if it was a sphere, you can just look at a uniformly rotating solution, and you can actually construct a uniform rotating black hole solutions. So that corresponds to rotating black holes. That's a kind of these things. But of course, you can do more other things. Like there are various kind of generalizations of these to superfluids and so on. Then you can ask, like what happens if you have vertices, right? Superfluids have very isolated vertices. How do those vertices continue into the 5th dimension? Okay, you can ask, like if you can take a heavy particle and then drag it through the fluid, okay, and then the fluid creates a wake. This particle creates a wake, okay, and then like you can ask how does that wake look like in the thing. So people have done these things. You can do it at the numerical level. Okay, you can construct the numerical solution of Einstein equations from a numerical solution of Navier-Stokes equations, but you can also look at analytical solutions and so on. Yeah.
So, for example, for the viscous fluids, one very common feature is that you can start with any velocity distribution, and in the end, it will come to rest.
Yes.
So, what does that correspond to in black holes?
In the black hole, it's a statement that if you kind of create any gravitational wave over the black holes and wait and don't do anything, eventually the gravitational waves will all fall into the black hole and the black hole will go quiet.
Okay.
Yeah, it's what is called a ring down of a black hole, as a gravitational wave people call it.
Okay, thank you.
Yeah. Sorry, and it's tightly connected to the Hawking area increase. The fact that fluids are dissipative and constantly increase their entropy and so settle down is, on the fluid side, exactly the Hawking area increase theorem. It says that the area of the black hole always increases.
Okay, thank you.
Yeah, maybe we should take the rest of the questions after the talk.
Oh, yeah.
Thanks
maybe.
a lot.
Oh, right, yeah, sorry.
Yeah, I mean, this was meant to be a 5-minute break.
Yeah,
So
sorry. Yeah. Okay, sorry. I think kind of, yeah. Okay, so let's kind of go to fluctuations. So the second part, okay, which I realize I've kind of eaten up a lot of my time, but okay, but it's okay. Right? The basic point here is to kind of give you the general idea. Okay. So, like now you can start asking about, okay, so you have some Navier-Stokes equations, some Einstein equations, some solutions here, map to solutions there. But what about, okay, if I want to think about fluctuating hydrodynamics? Okay. But before that, it is good to kind of say a bit about the linearized modes, okay, of a relativistic hydrodynamic equation like that, okay. So what happens if you kind of linearize this equation, this relativistic Navier-Stokes equations? So the linear modes, okay, are of two kinds, okay. They are first of all sound modes, which you get even in the Euler fluid, okay, which basically have some dispersion like this, okay, where Cs is the sound velocity, okay, which for a fluid which is scale invariant, E equal to 3p, okay, or E equal to in general d minus 1p, okay, is given by, so basically Cs square is given by something like del p by del E, okay, which is just 1 by d minus 1 for scale invariant fluids, or 1 by 3 in case of 3 plus 1 dimensional fluids, okay. So 1 by square root 3, okay. So Cs is 1 by square root 3, okay. So this is a dispersion for sound waves, this people know. And then once you add viscosity, okay, then this dispersion gets corrected, okay. So there's something called as a Stokes attenuation, okay. This is all compressible fluid dynamics, if you know. There's a bulk viscosity, shear viscosity. So the shriller modes die faster when you send the sound into the fluid and so on. Okay, so there's some Stokes attenuation, okay, due to eta. And if there's a zeta, then the zeta. But here we are talking about scale invariant fluid where there's no zeta. Okay, and then apart from that, okay, there are what are called shear modes, which are the modes that we are familiar with from incompressible fluid dynamics. Okay, so these are modes which are basically look like they are diffusive modes of momentum. The physics of them is diffusive. Okay, so this is of course is a linear dispersion. Okay, so this is a diffusive modes. Okay, this is basically diffusion of momentum. Okay, so you get something like, let me get the signs right. Yeah. So this gamma eta is some effective diffusion constant, which is proportional to eta. I will get. I'll tell you the explicit expressions in a moment. Okay. So the point is that like so this is basically coming from viscosity, the shear viscosity. Okay, and then you get it gets corrected. If you have higher derivative corrections, this gets corrected. Okay. So the basic linearized physics of these fluids is basically these two modes. Okay, so you have a wave mode, wave sound waves. Okay, and then you have a diffusive mode. Okay, which is the shear modes. Okay. Now, what that means is that like you can kind of think about. Okay, what this means is that the 2-point functions. So you can think about correlations. Okay. Maybe before that, let me kind of say what this corresponds to in the gravity. So in gravity, okay, so you again have two modes, okay, and the modes are basically given as follows. Okay, so there are, if you take this metric, okay, which is given by this h mu nu, okay, this v mu, h mu nu, and so on. What you can do is that you can kind of decompose them, v mu and h mu nu. Okay, you can decompose them in terms of the transfer space. That is, so you have, what are the two guys you have? So let's say you go to the rest frame of the fluid. Okay. Okay. And so if you have a mode, then you only have a ki, k vector. Okay. So the way you kind of can decompose them is that you can decompose them by, like the rotations, by how they behave under rotations about k. Okay. So decompose by, according to rotations about k, which makes sense in three dimensions. So k vector, let's say z axis, then you just have xy rotations. Okay. So then there are, like various kind of modes. You have a vector, scalar, and so on. Okay. So let's say k is along z direction. Okay. I can just take it to be along z direction. Okay. So then I have something like Vz, which is like a scalar under z rotations. Okay. And then I have Vx plus minus Ivy. Okay. Which rotate by e to the power plus I theta and e to the power minus I theta. So they have plus minus 1 spin, so to speak, under those rotations. Okay. H mu nu has, and then you have, of course, Vt, Vz, Vt. Okay. And then similarly, you have Hz, Htt. Okay. And then you have also Vr. Okay. And so on. Okay. So similarly, so you get the basic idea. The basic idea is that you kind of ZTR, they don't change under these rotations. Okay. Under this, in general, this is SO d minus 1 rotations, d minus 2 rotations. Okay. And when d is 4, 3 plus 1d, you have SO2 rotations about the k axis, and you can kind of decompose them. Okay. So what happens is that, like you can decompose these waves. So these are now gravitational waves. Okay. So these are gravitational waves. Okay. About this black, about the black hole. Okay. So then naturally under these, okay, in general you have a tensor, so you can have 3 parts. You can either have scalar, basically you can have either spin 0 or spin 1, okay, or spin 2, okay, under these rotations, okay. So it's sometimes called a scalar, vector, and tensor sector. It's about these rotations, okay, okay. What happens is that this guy, okay, dies out very fast. This guy basically goes to the sound mode. Okay. Okay. And this guy basically goes to shear mode. It's kind of intuitive because the sound mode exists in the scalar sector. It does not have a direction. It's a compression rarefaction. It does not have any polarization. Okay, so it's in the scalar sector. Okay, it's along the k, right? Sound propagation. Okay, there's no like compression rarefaction, only along k. Okay, so it doesn't have any. It's completely rotational invariant with respect to the wave vector. Okay, and hence it is in the s equal to 0 sector. Whereas the shear mode, okay, is like what we see in incompressible velocity, incompressible fluid dynamics. Okay, where you have a velocity vector such that its divergence is 0, which in Fourier space means that k dot b is 0. Okay, so it's a transverse vector. Okay, it's a vector which is perpendicular to the velocity. So the shear mode is a bit like electromagnetic waves, where it has some polarization perpendicular to the mode of the wave vector. Okay, and hence it's in s equal to 1. And this s equal to 2, okay, gravitational waves, they just die out very fast. Okay, so they don't become hydrodynamic modes. Okay, so this is kind of like another way to look at free gravity correspondence, where we are not looking at the full nonlinear solution and so on, but we are looking at linearized analysis about that and linearized analysis about here. Okay, and we are seeing that if you do the linearized analysis about this black hole, which is basically studying gravitational waves, okay, by perturbing these things, you see that certain gravitational waves quickly die down. Okay, they fall very quickly. Okay, very quickly, as in this time scale is given by this temperature. Okay, inverse temperature. Okay, and the point is that so some die down very quickly. Okay, within that time scale, and whereas some other modes, some gravitational modes linger. Okay, so usually these gravitational modes, they kind of linger. Okay, because for a while. Okay, and they slowly diffuse. Some of them travel like a sound. Some of them travel like a shear mode in a incompressible fluid. Okay, and that's what you see. Okay, which is also nice. Okay, which is a map between like what you see in linearized hydro and linearized gravity. Yeah. No, that's the point. The point is that like those modes don't survive the fluid dynamical description. Okay, and that is how it should be, because you see in fluid dynamics there is no tensor field, right? To start with, the basic fields of fluid dynamics are temperature and chemical potential, and velocity. Okay, so these are scalars and vectors. Okay, so you will never get any s equal to 2 if you decompose them. Okay, in terms of these rotations about the k vector. So you should not get any such modes, and indeed that is what happens when you solve the Einstein equations. The modes that with s equal to 2, which you can get in gravity, okay, those modes die very fast. Okay, s equal to 2 with respect to these transverse rotations. Okay, and the point is that like only the other two guys kind of linger on. Okay, and they get exactly mapped to these two dynamics, and their dynamics is very similar. In the sense that one of them evolves like has a linear dispersion, another has a quadratic dispersion, exactly like the sound mode and so on. So that's another way to kind of read off the sound velocity and viscosity and so on. Okay, by looking at the linear race analysis. Okay, yeah.
Yes. Is there any connection between some soft theorem and this fact?
Sorry?
Is there any connection between soft theorem?
Soft theorem. Okay, soft theorems. Okay, I don't quite understand soft theorems in ADS. Okay, when you have negative cosmic constants. Soft theorems usually we talk about in flat space time when you have some scattering and things go very far and so on. Things don't go very far in ADS. This is definitely low energy modes. Okay, but the soft theorems might be more related to actually, like some memory effects and fluctuations and so on. But this has never been very made precise. It is possible that there's some relation, but I do not know. Okay, but not at this level. This is just some linear S analysis. But once we take into account fluctuations and so on, once we take into Hawking radiation and things like that. Okay. By the way, this gamma eta is just given by eta over E plus P in general. Okay. Of course, E is 3P or D minus 1P in case of scale invariant fluids. Okay. So you have these. So linear hydro gives you these things. Now, once you have these linear modes, okay, then you can ask, how these modes, affect the dynamics. Okay. So in general, okay. So let's see.
So, Loga, maybe I can make one comment about the S equal to 0 and S equal to 1. These are related to no-hair theorems of the black hole, in the sense that, besides the mass charge and the angular momentum, nothing else survives. Anything that, like the spin 2, okay, this is not allowed by the no-hair theorem. There are no charges corresponding to those, so they just have to go away.
Sure. So no-hair theorem here basically means that the final dynamics is effectively described by energy momentum tensor. Okay, like because of the mass is described. Of course, in kind of contracting spacelines like ADS, actually you can also violate no-hair theorems. Okay, by cooling down black holes and making some clouds condense over them, which correspond to superfluids and things like that, okay, which maybe somebody will talk about. I don't know.
Excuse me.
Yeah.
It is possible to get hydrodynamics for smectic liquids or something which involves some tensors and all that.
Yes.
They will not correspond to anything in the gravitational context.
Yeah. So people have tried, to get these kind of things by putting some kind of a massive graviton. So not the usual graviton. Sometimes the usual gravitational waves correspond to energy momentum, but you could try to put some order parameter. You can do probably other things also, but I don't know whether there's a specific paper. But people do try to do that. Okay, I am more. Yeah, smectic crystals. I don't know whether anybody has done, but people do try to do kind of various kind of superconductors. Okay. Like where you have D wave and so on and so forth. Okay, for that they sometimes put some higher spin particles and see. Yeah, so there are some efforts like that. Okay, I'm not completely familiar with them, so I don't know like how well they work, but I do know that there are people who try to do such things. Yeah, but in this case, so this is true about the Einstein equation, the gravitational waves, right? Okay. Now you could kind of see you also need, yeah, the kind of thing that I was saying. in the sense that if you want some order parameter, right, either superfluid or some other order parameter, which kind of participates equally with the fluid dynamics, okay, what you have to do is that you have to kind of cool down the fluid, okay, you have to kind of spontaneously symmetry break and then get a Goldstone, okay, so which usually corresponds to cooling down the black hole sufficiently, which is dialing down its gravity a little bit, okay, such that it can have a cloud over it, okay, and you have to dial down its gravity because if black hole has sufficient acceleration due to gravity, it just fall. Okay, so you kind of dial up the gravity. That's a phase transition. Okay, some second order phase transition where if you dial up the gravity, and this is related to Hawking's statement that the surface gravity of the black hole corresponds to the temperature. So as you dial up the surface gravity, the temperature becomes higher, the black hole heats up, and then it gobbles up any cloud, and the no-hat theorem becomes a very good description. But if you dial it down, if you cool the black hole by basically kind of dialing down the gravity, you can do it by charging the black hole. Okay, for example, okay, because then you can kind of play your Coulomb repulsion against your gravitational attraction and then put a charge cloud over it. Okay, and that kind of phases, then you can study and modes around that. Okay, as you would expect, they are broken phases. By Goldstone theorem, they are Goldstone modes. They participate in the fluid dynamics. They have these long-lived modes which kind of live in those clouds. Okay, yeah. So here I'm just talking about the simplest case. Okay.
Sorry, just to add to that, string theory generally has lots of fields at the bulk. These solutions are solutions of a universal truncation that keeps very few fields. What Loga talked about just keeps the graviton. All the other fields are set to 0. These other solutions Loga is talking about are solutions in which more fields are turned on and condense. And then you can have more interesting data.
Yeah. That's it. Sorry, I think this clock has just disappeared, but anyway, I think it's a bit dangerous to leave me without a clock. But okay. But anyway, yeah. So anyway, so the point here is that so good. So the point is that so you have some modes in the fluid dynamics, okay, and then you have some modes in gravity, okay, and the point here is that once you have these modes, okay, you can kind of talk about at this linearized level, you can talk about fluctuations in these modes, okay, in the sense. Okay, so in the fluid dynamics, what you can do is that you can kind of, so these are solutions of ordinary Navier-Stokes equation. Okay, so what you can go is that you can go from Navier-Stokes equation, you can go to Navier-Stokes equation with noise, which is basically fluctuating hydro. Okay, at the linearized level, you just add some noise. Okay, and so what you can do is that. And you can kind of, like what you do with the Langevin theory and so on and so forth. So you have some equations and then you add the noise and you make sure that the noise obeys FDR. Okay. So what that means is that, you have, you have a noise. So this noise, basically obeys any kind of, sorry. Yeah, so it obeys, at linearized level. So this is just linear FDR. Okay, that's what I mean. Okay, something like this thing. So what you can do, for example, is that this diffusion you can add a noise. Okay, and then you can say the shear mode has a noise, and the noise, okay, has a spectrum. It's a Gaussian noise. Okay, this is a natural thing to do at the linearized level. Okay, and its Gaussian noise. Okay, its strength is basically determined by, eta and so on. Okay, so that's what you can do. Okay, and once you add that, okay, you can ask what happens. Okay, so I won't kind of go through various things about fluctuating hydro, but one of the things that happens is that once you add these once you do these noisy Navier-Stokes equations and do fluctuating hydro, okay. So what happens is that you get what is called as long time tails. Okay, there are very, very many other things you get. Okay, but let me just talk about this particular phenomena. Okay, so long time tails are basically the statement that, you know, like if you have, so ordinarily in usual fluid dynamics, if you kind of excite something, okay, let's talk about just let's say incompressible fluid dynamics. If you excite something, then this is like a diffusive dynamics, and you expect that, you know, things die out in a diffusive way, right? You know what that means is that something like you get some e to the power minus k square t kind of you know, fall off for a mode with wave number k. Okay, right? So that's the standard diffusive behavior. But the point here is that, like, once you add noise, okay, these fluctuations can be very long-lived, and they can kind of, you know, like destroy these kind of fall-offs. So one way to kind of say it is to kind of write down this particular equation. So let me kind of write it down, and then I'll tell you what it is. Okay. And I'll also tell you where you can find the calculation, since I'm not going to do the calculation here. Okay. This looks like, so I'm using the same notation. D is the space-time dimensions. Okay. Into gamma S. So this tau is this tau. Okay. Right. Yeah, some of you might know this in 3+1 dimensions. Okay, this is like this famous 3/2. Okay, in energy density. You have gamma eta. Okay. Okay. So basically, the statement here is that. So what are we looking at? I'm looking at something like XY. Okay. Some shear correlations. Okay. And I'm asking, how does the at large tau? I'm looking at, you know, like what happens to these correlations. Okay. At so this is like a classical correlation. So this is not in the fluid dynamical, in the classical stochastic theory. Okay. Stochastic fluid dynamical theory. Okay. Yeah. So maybe I will write down the reference from which I take this. So so these long time tails in relativistic fluid dynamics was worked out by in a paper by Gautam and Yaffe. Okay, who's in this FDH 0303010. Okay, they worked it for 3+1. It was generalized to, you know, like general D and many of the things I'm going to say about fluid, the gravity side was pointed out by Karen Howard and Saremi. Okay. In a paper that they wrote, 0909.4525. Okay. So they also look at charged fluids and what happens to charged fluids and so on. So they say various things. Actually, they kind of derive, they kind of describe the derivation. The derivation basically roughly, you know, in the, for a field theorist, basically looks like this, a 2-point, you know, function. Okay, so you have a txy, and then you have some, you know, fluid loop modes in the loop. Okay, which kind of, so when you do the stochastic theory, okay, and when you do the averaging over the noise, okay, you get these loops, okay, in the stochastic field theory, and then you calculate that loop, okay, and you get this long time behavior because the fluid modes are very long lived, right? You know, long time behavior in this conserved quantities, okay. So gamma eta I have already written, okay. This is for a general fluid, okay. And gamma S is really it's the Stokes attenuation constant, okay, which is given by, for a general relativistic fluid, by this formula. Okay. It's okay. I mean, it's just to say that there are very specific prediction, right? Okay. of fluctuating hydro. So this is a prediction of linearized fluctuating hydro. Of course, relativistic, the kind of hydro I was talking about. Okay. So there's a prediction which says that I'm missing some. Yeah, maybe it's okay. Yeah. Note that these, so these are kind of power law tails. Okay, so these are power laws. Okay, that's the thing you have to know. So in some sense, like if you did not have fluctuating hydro in ordinary hydro, okay, you would expect this exponential fall off, like in the diffusion equation, e to the power minus k square tau kind of thing, like e to the power minus gamma eta k square tau. If you have a diffusion equation like that, okay, right? That's a typical thing. Which so the mode which is diffuses basically dies down, okay, like that, okay. And the higher the k, it dies down faster. That's the physics of diffusion, okay. But if you have fluctuations, okay, there's a power law fall off of this. If you look at this integral, so this is a spatial integral, right? Just of the shear tensor. Okay. So, which is completely decided by things that we already know. Okay, and there is a question whether fluid gravity can reproduce this. Okay, right? You can ask these kind of long-term tails, okay, whether fluid gravity can reproduce or not. Okay, so that's an interesting question to ask. Okay, and you can ask, like what would you do on the black hole side, okay, to even start thinking about these things. Okay, so this is a question that these guys kind of address. I mean, this is in the same decade where fluid gravity and so on was developed. Okay, so they try to at least at this linearized level, okay, especially Karen Huart and Cergy, okay, in this paper in 2009, okay, they kind of gave a kind of an answer, okay, which is okay. So they said something like this. Okay, so this is they said, okay, so you take this black brane or whatever black hole, okay, that I have been talking about. Okay, so this is where the fluid is, and this is the black hole. Okay, this is outside. Okay, they said that you can kind of see, this. We kind of know where this comes from in the fluctuating hydro. It comes from letting the hydro modes run in loop. Okay, so to speak. Okay, and then they said, see, we know from this mapping, what I've described, that the hydro modes, the shear modes and the sound modes, are really certain kind of gravitational waves. Okay, gravitons, if you want. Okay, and like if you can let gravitons also go in a loop, that is, you start calculating the effect of graviton loops in the bulk. Okay, this was their idea. Okay, then it basically amounts to kind of doing what you do in the fluctuating hydro. Okay, and and you should be able to reproduce it. Okay, so this is the basic point. The point is that so you have some, if you want, like there's some two places where the Txy is introduced. Okay, in the space-time. Okay, and you're calculating some two-point function. Okay, and what you could do is that you could kind of think about some gravitational wave, going down, and these gravitational waves kind of interacting. Of course, gravitational waves self-interact. Okay, there's a nonlinear part of Einstein equations. They interact with each other. Okay, and you have some graviton loop. Okay, so this is like a, okay, this is like a effect of, if you want, quantum gravity. Okay, where you kind of let the gravitons run in the loop. Okay, and you know, like so what they, so this was the basic idea. Okay, so is the idea clear? And the point is that, you know, and you want, of course, these things to be very well separated. Okay, so because you're looking at large tau. Okay, so you're looking at very separated. Okay, and when you, maybe you should not draw it like that. Okay, you should think of it as, you know, maybe something, you know, some very well separated 2-point function. Okay, and then, you know, like they said, they argued, okay, that this graviton loop in this limit, okay, at large tau, okay, basically get contributions only from the near horizon.
Loga, the propagators in this loop, what were their boundary conditions at the horizon? What were the boundary conditions of the propagators in this loop at the horizon?
Yeah, so if you look at Karen-Huat-Saremi, okay, they are a bit distinct. See, the point is that, yeah, the point is that, you know, like when Karen-Huat-Saremi were doing this, essentially they are, what they do is like, they say the propagators become fluid mode propagators with those fluid poles, okay, in this limit. And then they say, okay, so then the loops of gravitons basically have the same propagators as basically they reduce this whole calculation to this calculation, to the boundary calculation. Okay, they try to make an argument. Okay, we can ask, you know, like how well is this argument? So what the point here is, but this is really the point. The point here is that I'll come to some of the subtleties in this calculation, but their basic idea, okay, was that somehow, okay, you should be able to make sense out of the diagram in such a way that this loop, okay, becomes this, okay, and actually this loop has to be, you know, like okay. So one way to say it is that it's not actually the retarded loop, okay, because this 2-point function, okay, if you think about it in terms of quantum field theory, okay, so if you think of these as quantum field theoretical operators in some underlying quantum field theory, then I can't just say this, okay, I have to tell you what is ordering and so on, right? Okay, because these are operators, okay, are they time ordered, are they anti-time ordered, are you calculating the commutator, are you calculating the anti-commutator, okay? So they said that what this does is that it's calculating fluctuations. So it, you know, it actually is you know, in the quantum theory, it computes as the anti-commutator. Okay, so which is what, so which is not the retarded correlation function, because retarded correlation functions are response functions. If you, for those of you who know Kubo formula and so on, okay, they involve commutators of stress tensor. Like if you want to calculate Kubo formula for viscosity, okay, you look at the commutator of the stress tensor. So this is an operator which is not part of the retarded, you know, like propagator, but that's the computation you have to do, okay, to get that answer, okay, and then they wrote down some propagators to kind of, you know, like okay, say that this thing, okay, so you can look at the argument, okay, but this particular question that Shiraz asked is actually very important, okay, because, you know, like when you start looking at these anti-commutators, okay, what you're looking at, let's just, you know, like say some basic analogy. Let's say, you know, if you're having some harmonic oscillator, okay, and you're looking at the anti-commutator of AA DAG, okay, right, okay, okay, maybe 5 more minutes, yeah. So the point is that expectation value of commutators, okay, is just gives you some spectral function. It just gives you the, you know, if you have many number of harmonic oscillators, it just gives you the number of harmonic oscillators. Okay, but if you have anti-commutators, especially if you calculate it in some thermal state, okay, what you will get is basically, like something like 2 times the Bose-Einstein function plus 1. Okay, this is 1, and then in the normalization that is 1. Okay, if that is some function, then this will be some function. If you have a set of harmonic oscillator, if you have some spectral function or something. Okay, so the anti-commutators actually tell you about the distribution or the fluctuations about the thermal state. In some sense, it gives you some more microscopic this thing, and basically, so to get this anti-commutator, you have to get a Bose-Einstein distribution out of it. Okay, which basically means that you are looking at what are looking at thermal gravitons. Okay, so what contributes to this, okay, are thermal gravitons. Now you can ask, okay, in fluid there's a finite temperature. Where do thermal gravitons come from? The black hole? Of course, the black hole also there's a finite temperature, because Hawking told us there's a Hawking radiation. But this is not a completely classical effect. It comes if you kind of, in this case, quantize gravity a little bit. Okay, so you get Hawking gravitons. Okay, okay. So the point here is that so you have to basically deal with this Hawking radiation, and the fluctuating hydro. Okay, basically the modeling of the fluctuating hydro. Okay, is basically is related to understanding, okay, how Hawking gravitational waves, that is, these are not gravitational waves that classical GR people study, but because black hole is a thermal thing, okay, even a black hole which is completely, quiet, from a macroscopic point of view, it has a noise. Like what happens if you have a fluid which is at rest, okay, you put a Brownian particle, you can see that it's being kicked around, right? Okay, there's a Brownian noise, and the noise is because there's a microscopic jiggling around, okay, of the fluid, this thing, and there's a microscopic noise which is kind of, and similarly, okay, even a black hole which is quiet is kind of emitting these Hawking gravitational waves. Okay, it's kind of having this noise of noisy gravitational waves, okay, which are coming from the fact, not from classical GR, okay, but it is coming from the fact that if you quantize gravity a little bit, in the sense that you perturbatively quantize, okay, then you kind of understand that black hole is like a finite temperature bath, okay, and there are gravitons jumping in and out. Okay, so the point here is to kind of so this is the basic this thing. So this basically links this kind of a thing in fluctuating hydro, okay, to effects of Hawking radiation. Unfortunately, I've run out of time, but the basic thing, maybe when Mukund comes, he can talk about some of the work that we've done, is to kind of try to make these statements precise. Okay, one is to try to make this even the linearized statement precise. Okay, and I think so over the last few years, I, Mukund, and various people have actually made this statement precise. Okay, there's a way to make this precise by kind of separating out the fluctuations and classical gravitational waves separately. Okay, in some systematic way. Okay, and then you can at least show that these things exist. Okay, the point here is that we have not. So there are various kind of statements actually Karan Sarami make, that there are these two kinds of modes. Then these modes kind of this loop basically dominates only the near horizon and so on. Okay, it's a very clever kind of approximation or whatever you call it. Okay, to get the answer they want. Okay, and it's kind of probably right because they get what the hydrodynamics predicts. But there is a lot of things to be understood how to make this precise. Okay, and how to make these kind of statements precise, that these fluctuations work and so on. So we have a way of actually thinking about these long-lived fluctuations, which I can't talk about, but maybe I will give you some references. Okay, you guys can have a look at it, where we talk about the shear and sound mode fluctuations. Okay, in a set of papers. Okay, so 2012.03 999 and 22, not 2 dot not 4, 079. Okay. So in these two papers, okay, with various authors, okay, we kind of, like looked at this kind of a setup, and we kind of linearized it, and we studied the Hawking radiation in these guys, okay, and we kind of showed that there are long-lived Hawking radiations which can contribute to these loops, okay. But there's a question of, like how do you calculate these loops, and how do you kind of show that this horizon domination actually works, okay. There's a broader question, which is the thing that I've started my talk with, okay, which is to kind of take this whole setup, okay, and then do a nonlinear generalization. This has not been done, okay, mainly because these calculations are a bit, look a bit horrible, okay. But so we are just really getting down to it, okay, shoring up our courage to just calculate all the terms, okay. But the point is that but in principle, I do think that in this fluid gravity, like if you calculate these fluctuations properly, okay, you would kind of answer both these questions, which is how do these fluctuations of gravitational waves about this black hole look like on one hand, okay, and what does that say for the fluid dynamics on the other side, okay, and how do you kind of see this is also kind of linearized analysis, okay, which is here, but the question is that like how do you take into account nonlinearities of fluid dynamics and nonlinearities of fluctuations and so on. Okay, so that's so with that note, I'll just end, and thanks for listening. Yeah, I'll take some.
This fantastic talk. Just to say that you have ended like these, the serial episodes where the next episode, appears also to be very interesting. So the next episode is at 3:45. That's the discussions led by Loga. So please come to that. So Loga will explain everything about Hawking radiation, etc. in that as well. So thank you, Loga.
Yeah, probably also Mukund will also talk about it.
Mukund will also talk about this, and there will be a separation of about 11 days between these two talks. So
it is double the number of weekly series. Yeah.
So a lot of questions have been asked, but if there are some 2 or 3 absolutely pressing questions, they can be asked now. Yes, please.
Usually in the hydrodynamics, in the classical case, you'd find that also there is correlation in the space. So if you write Tx, x prime.
Yes.
Now, given that your integral is finite, it's just going, because those would also be a power law. So could you say something about the equal time correlations on space?
Yeah, so equal time correlations, yeah, so those depend on initial. Okay, so the point is that in relativistic hydro, okay, in some sense, equal time correlations are harder because it's a causal theory, okay, but you can have it. But the question is, okay, so you have to start with some initial state, okay, and then you are looking at equal time correlations, or because if you just take thermal state, okay, and you look at T, okay, you would. Yeah, it will commute. I guess you will get some thermal correlations. Yeah, so that will be captured by some Euclidean field theory, the thermodynamics of these things. Is that? But it won't contain any tails. Okay, maybe I'm not very clear. Okay, let's see. So let's take a quantum field theory. Okay, so this is calculated at some finite temperature state, some perturbation, right? Okay, and then so let's take a quantum field theory in thermal state. Okay, and then let's say you look at equal time correlation functions. These equal time correlation functions actually all die exponentially, okay, in space. Okay, this is basically the physics of device screening. Okay, everything gets device screened. Okay, at equal times. There are no, or another way to say it is that if you look at the Euclidean field theory, okay, everything gets capped. Okay, and then you get basically local theory. Okay, where things correlation just die down exponentially. So there's no power law there, or I mean, yeah.
Unless you put some
yeah, then you can kind of, yeah, you can, okay, what you can do is like you can cool it down, then you can condense something, and then you can do something. But yeah, but at least at high temperatures, this is the expectation. Yeah.
Any other questions?
Okay.
Oh, okay, so let's thank Loga again for a great talk.